Land use management obviously has to include agriculture, which is a huge fraction of human activity in terms of land use. Here comes my favorite chopper. So let's quickly look at agricultural activities and greenhouse gas emissions. Agriculture is the largest contributor of non-CO2 greenhouse gases. Right? So if you think about methane, nitrous oxide, obviously agriculture contributes a lot. So 56% of the non-CO2 emissions in gigaton CO2 equivalent here come from agricultural activities. Okay, food system emissions contribute 19 to 29% of the total greenhouse gas emissions. The whole food system, production, processing, transportation, consumption, waste, etc. They contribute almost on average 25% of the total greenhouse gas emissions. Okay, so livestock also contribute 7,100 million ton CO2 equivalent per year, or 14.5% of the total greenhouse gas emissions. Something to worry about. We already talked about their special many, like cattle, have this special ruminant stomach structure, which is very inefficient thermodynamically and produces methane in their belching, I suppose, both ends. Agriculture is responsible for 75% of the global deforestation. That's an indirect effect on greenhouse gas emissions as well. If trends continue, about 10 million square kilometers of land will likely be cleared by 2050 to meet the food demand. That will result in 3,000 million tons of CO2 equivalent per year. But this depends on population projections, which tend to have a bit of uncertainty, especially in terms of educating women and them having fewer kids. Doesn't say much about consumption levels, but usually food demand is related to populations, and populations are always projected to increase in the UN projections. Alternative pathways would only require about 2 million square kilometers of land to be cleared, and that would reduce the emissions to 1,000 million ton CO2 equivalent per year. There is a good opportunity to bend the curve, right? Here is again a picture of the soil in Iowa. I think the corn you can see here, roots going quite deep, and you can again see the soil structure, more fine structure with darker colors. There is coarser structure here with less carbon visibly to see here. But it shows you the vertical inhomogeneity and obviously horizontal inhomogeneities. So estimating global carbon stocks is not an easy task, but people still do bold estimates based on all the data, often combined with models of various types. So this is showing a map of soil organic carbon content going from 0 to 7.5 kilograms per meter squared, so organic carbon content by weight, and the darkest colors here are greater than 90 kilograms per meter squared. I had mentioned permafrost before, so you can see these regions where soil was not shown when we looked at the erosion maps, or degradation maps, but soil carbon content can be very high in those frozen soils. Permafrost is basically frozen soils with heavy freezing below the surface and seasonal variations in freezing in some places based on how warm spring and summer get. And you obviously see glaciers here, deserts up here, all the way into Mongolia, and large deserts down here, rainforests with high soil organic content, and so on. And if you look at by climatic regions for soil organic content in kilograms per meter squared and carbon stock, you will see hyper-arid, arid, semi-arid, dry, humid, dry, subhumid, dry, and humid. Obviously you expect humid regions to have larger amounts of carbon content per unit area, as well as carbon stock. Okay, so these are percentiles and the range. Obviously the uncertainties are high, and keep this map in mind, especially this region, for example, and look at this soil inorganic content. So now soil inorganic content is high in these desert areas because it is produced by various erosion processes of conversion of rocks and minerals into soil. So soil inorganic carbon content is half the range here. Maximum is only around 45 kilogram per meter squared, whereas the organic carbon was greater than 90 kilogram per meter squared. And here also you change the scales of soil inorganic carbon content. Hyper-arid and arid regions have high inorganic carbon content, whereas humid regions have smaller density and smaller stock. For whatever reason, dry regions here show up as large, potentially because they may have enough vegetation to create accelerated weathering of the rocks to produce minerals and inorganic carbon. I'm just guessing, but that gives you a good sense of how greenhouse gas emissions from soils could be related to vegetation types, climate, soil types, and so on.